A railroad tie has three jobs. It holds the two rails at the correct distance apart, a measurement called gauge. It transmits the enormous vertical load of a passing train down through the ballast and into the earth, and it anchors the entire track structure against lateral and longitudinal movement. If any one of those three functions fails, the result is a derailment. For over a century, railroad ties were made of hardwood. Oak, Douglas fir. They rotted, they split, they lasted 20 to 30 years at best. But wood fails visibly. A section crew walking the track can see the decay, feel the softness, and hear the hollow ring of a bad tie under a hammer. In the 1960s, the railroad industry began replacing wood with pre-stressed concrete. The promise was a 50-year service life, heavier axle load capacity, and near-zero maintenance. By the 2000s, over 30 million concrete ties had been installed across North American track alone. The engineering behind them is elegant. High-strength steel tendons are stretched to roughly 75% of their ultimate tensile strength, around 270,000 pounds per square inch, and concrete is cast around them. When the concrete cures and the tension is released, the steel tries to contract. The concrete resists. That tug of war puts the entire body into compression, preloading it against the bending forces of a passing locomotive. Concrete is strong in compression, but weak in tension. Pre-stressing solves that problem. Or it was supposed to. The most insidious failure mode hiding inside these ties is a chemical process called alkali-silica reaction, ASR. Certain forms of silica in the aggregate react with alkali hydroxides in the cement. The reaction produces a gel that absorbs moisture from the environment. When it absorbs moisture, it swells. Inside a tie already under enormous pre-stressing forces, that swelling creates internal pressure. Microcracks form first. Then those cracks propagate along the plane of the steel tendons, where stress concentrations are highest. The bond between steel and concrete weakens, the pre-stress relaxes, and the tie loses its structural integrity from the inside out. On the surface, all that appears is a faint web of cracks. Engineers call it map cracking. It looks almost decorative. It is the signature of a tie that is already dying. A Federal Railroad Administration study examined ties on the Northeast Corridor manufactured in the 1990s and confirmed horizontal splitting along the top row of tendons, driven by ASR-induced expansion. These ties were not failing because the trains were too heavy. They were failing because the concrete was destroying itself. A related mechanism, delayed ettringite formation, compounds the problem. Ettringite is a mineral that normally forms early during cement hydration. But when concrete is steam-cured at excessive temperatures to speed up production, ettringite formation is suppressed and then occurs later, after the concrete has hardened. Late-forming crystals expand inside the matrix and cause cracking that is nearly indistinguishable from alkali-silica reaction. Metro-North Railroad in the New York metropolitan area installed roughly 50,000 concrete ties in the mid-1990s. Every single one had to be removed. New Jersey Transit lost 27,000 ties to the same defect. But chemistry is not the only threat. There is a purely mechanical failure called rail seat deterioration. Every time a wheel passes over a tie, it pushes the rail into the concrete surface. Between them sits a thin polymer pad. Under repeated loading, moisture infiltrates that interface. The pumping action of passing wheels creates a slurry that grinds away the concrete. For each millimeter of material lost, the fastener loses approximately 100 pounds per square inch of clamping force. As the grip weakens, the rail begins to tilt outward, and the gauge widens. When it exceeds tolerance, the wheel can drop inside the rail. That is a derailment. The most devastating real-world consequence of these failure modes occurred on June 3, 2022. A double-decker regional train derailed at Bergrain outside Garmisch-Partenkirchen in the German Alps. 5 people were killed, including a 13-year-old boy and 2 Ukrainian refugees. 72 people were injured. 3 carriages plunged down an embankment. The cause was defective pre-stressed concrete sleepers. Chemical degradation had destroyed their load-bearing capacity. On a curve where lateral forces peak, the damaged sleepers shifted under the train. The gauge widened and the train left the track. Deutsche Bahn, the German national rail operator, had known about the problem. A fault report for defective sleepers on that exact stretch of track had been filed 2 years earlier. An independent investigation spanning 3 years, involving more than 60 interviews and 10 million data points, concluded the accident was preventable. The report implicated board members of Deutsche Bahn's infrastructure subsidiary. After the disaster, Deutsche Bahn initially estimated 200,000 ties might be affected. Then they discovered that a specific type of aggregate rock was a contributing factor, and the inspection program expanded. In 2023 alone, approximately 480,000 concrete sleepers were replaced, 6 times the normal annual rate. This is the fundamental paradox of concrete tie failure. Wood ties fail where you can see them. Concrete ties fail where you cannot. Alkali-silica reaction, delayed ettringite formation, and rail seat abrasion all progress beneath the surface long before they show up as visible cracks or measurable gauge changes. The Federal Railroad Administration has developed gauge restraint measurement vehicles that stress test ties without removing them. But this is specialized, expensive equipment. It cannot cover 140,000 miles of track continuously. Meanwhile, the loads keep climbing. Heavy haul corridors push 33 tons per axle over infrastructure that was often designed for less. Modern operating philosophies favor fewer, longer, heavier trains. Every car in a mile-long consist hammers the same 3,000 ties per mile, the same fasteners, the same rail seats, mile after mile, day after day. The concrete railroad tie was supposed to be the permanent solution, the end of the century-long cycle of rot and replacement. Instead, it introduced failure modes that are harder to detect, more expensive to fix, and in the worst cases, fatal. Somewhere in track that is wet and loaded and stressed, in ties poured with the wrong aggregate or cured at the wrong temperature, the GL is still forming, the cracks are still growing, and the gauge is widening by fractions of an inch that no one has measured yet.